you have co-authored several recent papers that sort of weave beautifully between the world of neuroscience and artificial intelligence. And this maybe, if we could, can we just try to dance around and talk about some of them? Maybe try to pick out interesting ideas that jump to your mind from memory. So maybe looking at, we were talking about the prefrontal cortex, the 2018, I believe, paper called Prefrontal Cortex as a Meta Reinforcement Learning System.
Yeah.
What is there a key idea that you can speak to from that paper?
Yeah, the key idea is about meta-learning. So
what is meta-learning?
Meta-learning is, by definition, a situation in which you have a learning algorithm, and the learning algorithm operates in such a way that it gives rise to another learning algorithm. In the earliest applications of this idea, you had one learning algorithm sort of adjusting the parameters on another learning algorithm. But the case that we're interested in this paper is one where you start with just one learning algorithm, and then another learning algorithm kind of emerges out of thin air. Mm-hmm. I can say more about what I mean by that. I don't mean to be, obscurantist.
Yeah.
But that's the idea of meta-learning. It relates to the old idea in psychology of learning to learn. Situations where you have experiences that make you better at learning something new. Like a familiar example would be learning a foreign language. The first time you learn a foreign language, it may be, quite laborious and disorienting and novel. But if let's say you've learned two foreign languages, the third foreign language obviously is going to be much easier to pick up. And why? Because you've learned how to learn. You know how this goes. Okay, I'm going to have to learn how to conjugate. I'm going to have to. That's a simple form of meta learning, right? In the sense that there's some slow learning mechanism that's helping you kind of update your fast learning mechanism. Does that
makes
bring it
sense.
into focus?
Yeah. So how, from our understanding, from the psychology world, from neuroscience, our understanding how meta learning might work in the human brain, what lessons can we draw from that we can bring into the artificial intelligence world?
Well, yeah. So the origin of that paper was in AI work that we were doing in my group. We were looking at what happens when you train a recurrent neural network using standard reinforcement learning algorithms. But you train that network not just in one task, but you train it in a bunch of interrelated tasks. And then you ask what happens when you give it yet another task in that sort of line of interrelated tasks. And what we started to realize is that a form of meta learning spontaneously happens in recurrent neural networks. And the simplest way to explain it is to say a recurrent neural network has a kind of memory in its activation patterns. It's recurrent by definition in the sense that you have units that connect to other units that connect to other units. So you have sort of loops of connectivity, which allows activity to stick around and be updated over time. In psychology, in neuroscience, we call this working memory. It's like actively holding something in mind. And so that memory gives the recurrent neural network a dynamics, right? The way that the activity pattern evolves over time is inherent to the connectivity of the recurrent neural network. Okay, so that's idea number one. Now, the dynamics of that network are shaped by the connectivity, by the synaptic weights. And those synaptic weights are being shaped by this reinforcement learning algorithm that you're, training the network with. So the punchline is, if you train a recurrent neural network with a reinforcement learning algorithm that's adjusting its weights, and you do that for long enough, the activation dynamics will become very interesting, right? So imagine I give you a task where you have to press one button or another, left button or right button. And and there's some probability that I'm going to give you an M&M if you press the left button, and there's some probability I'll give you an M&M if you press the other button. And you have to figure out what those probabilities are just by trying things out. But as I said before, instead of just giving you one of these tasks, I give you a whole sequence. I give you 2 buttons and you figure out which one's best. And I go, good job. Here's a new box. 2 new buttons. You have to figure out which one's best. Good job. Here's a new box. And every box has its own probabilities and you have to figure it. So if you train a recurrent neural network on that kind of sequence of tasks, what happens, it seemed almost magical to us when we first started kind of realizing what was going on. The slow learning algorithm that's adjusting the synaptic weights, those slow synaptic changes give rise to a network dynamics that the dynamics themselves turn into a learning algorithm. So in other words, you can tell this is happening by just freezing the synaptic weights, saying, okay, no more learning, you're done. Here's a new box. Figure out which button is best. And the recurrent neural network will do this just fine. There's no, it figures out which button is best. It kind of transitions from exploring the 2 buttons to just pressing the one that it likes best in a very rational way. How is that happening? It's happening because the activity dynamics of the network have been shaped by this slow learning process that's occurred over many, many boxes. And so what's happened is that this slow learning algorithm that's slowly adjusting the weights is changing the dynamics of the network, the activity dynamics, into its own learning algorithm. And as we were kind of realizing that this is a thing, it just so happened that the group that was working on this included a bunch of neuroscientists, and it started kind of ringing a bell for us, which is to say that we thought, this sounds a lot like the distinction between synaptic learning and synaptic memory and activity-based memory in the brain. And it also reminded us of recurrent connectivity that's very characteristic of prefrontal function. So this is kind of why it's good to have people working on AI that know a little bit about neuroscience and vice versa, because we started thinking about whether we could apply this principle to neuroscience. And that's where the paper came from.
So the kind of principle of the recurrence they can see in the prefrontal cortex, then you start to realize that it's possible for something like an idea of a learning to learn emerging from this learning process, as long as you keep varying the environment sufficiently.
Exactly. So the kind of metaphorical transition we made to neuroscience was to think, okay, well, we know that the prefrontal cortex is highly recurrent. We know that it's an important locus for working memory, for activation-based memory. So maybe the prefrontal cortex supports reinforcement learning. In other words, what is reinforcement learning? You take an action, you see how much reward you got, you update your policy of behavior. Maybe the prefrontal cortex is doing that sort of thing strictly in its activation patterns. It's keeping around a memory in its activity patterns of what you did, how much reward you got, and it's using that activity-based memory as a basis for updating behavior. But then the question is, well, how did the prefrontal cortex get so smart? In other words, where did these activity dynamics come from? How did that program that's implemented in the recurrent dynamics of the prefrontal cortex arise? And one answer that became evident in this work was, well, maybe the mechanisms that operate on the synaptic level, which we believe are mediated by dopamine, are responsible for shaping those dynamics.
So this may be a silly question, but because this kind of several temporal sort of classes of learning are happening, and so the learning to learn emerges, can you keep building stacks of learning to learn to learn, learning to learn to learn to learn to learn, because it keeps, basically abstractions of more powerful abilities to generalize, of learning complex rules.
Yeah.
Or is that's overstretching the this kind of mechanism?
Well, one of the people in AI who started thinking about meta learning from very early on, Jürgen Schmidhuber, sort of cheekily suggested, I think it may have been in his PhD thesis, that we should think about meta learning.
Yeah.
That's really what's going to get us to true intelligence.
Certainly there's a poetic aspect to it, and it seems interesting and correct that kind of levels of abstraction would be powerful. But is that something you see in the brain? This kind of, is it useful to think of learning in these meta way, or is it just meta learning?
Well, one thing that really fascinated me about this mechanism that we were starting to look at, and other groups started talking about very similar things at the same time, and then a kind of explosion of interest in meta learning happened in the AI community shortly after that. I don't know if we had anything to do with that, but I was gratified to see that a lot of people started talking about meta learning. One of the things that I like about the kind of flavor of meta learning that we were studying was that it didn't require anything special. It was just, if you took a system that had some form of memory, that the function of which could be shaped by pick your RL algorithm, then this would just happen.
Yes.
Right. I mean, there are a lot of there are a lot of meta learning algorithms that have been proposed since then that are fascinating and effective in their domains of application. But they're engineered. They're things that somebody had to say, well, gee, if we wanted meta learning to happen, how would we do that? Here's an algorithm that would. But there's something about the kind of meta learning that we were studying that seemed to me special in the sense that it wasn't an algorithm. It was just something that automatically happened if you had a system that had memory and it was trained with a reinforcement learning algorithm. And in that sense, it can be as meta as it wants to be, right? There's no limit on how abstract the meta learning can get, because it's not reliant on a human engineering a particular meta learning algorithm to get there. And that's, I also, I don't know, I guess I hope that that's relevant in the brain. I think there's a kind of beauty in the ability of this emergent,
the emergent aspect of it.
Yeah, it's something
as opposed to engineered.
Exactly. It's something that just happens in a sense. In a sense, you can't avoid this happening. If you have a system that has memory and the function of that memory is shaped by reinforcement learning, and this system is trained in a series of interrelated tasks, this is going to happen. You can't stop it.
As long as you have certain properties, maybe like a recurrent structure to.
You have to have memory. It actually doesn't have to be a recurrent neural network. A paper that I was honored to be involved with even earlier used a kind of slot-based memory.
Do you remember the title? Just for people who are interested.
It was memory augmented neural networks. I think the title was meta learning in memory augmented neural networks. And it was the same exact story. If you have a system with memory, here it was a different kind of memory, but the function of that memory is shaped by reinforcement learning. Here it was the reads and writes that occurred on this slot-based memory. This will just happen. And so this brings us back to something I was saying earlier about the importance of the environment. Mm-hmm. This will happen if the system is being trained in a setting where there's like a sequence of tasks that all share some abstract structure. Sometimes we talk about task distributions, and that's something that's very obviously true of the world that humans inhabit. We're constant. Like if you just kind of think about what you do every day, you never do exactly the same thing that you did the day before, but everything that you do is sort of has a family resemblance. It shares structure with something that you did before. Yeah. And so, the real world is sort of, saturated with this kind of, this property. It's endless variety with endless redundancy. And that's the setting in which this kind of meta learning happens.
And it does seem like we're just so good at finding, just like in this emergent phenomenon you described, we're really good at finding that redundancy, finding those similarities, the family resemblance. Some people call it sort of, what is it? Melanie Mitchell was talking about analogies. So we're able to connect concepts together in this kind of way, in this same kind of automated emergent way, which there's so many echoes here of psychology, neuroscience, and obviously now with reinforcement learning with recurrent neural networks at the core.